Let's look at the mux 3. A number of m:1 multiplexer can be arranged in a tree topology to obtain a bigger n:1 multiplexer is called as a multiplexer tree where n is greater than m. Bigger multiplexer can be obtained by combining smaller multiplexers. It is also common to combine to lower the order of the multiplexers like 2:1, 4:1 mux to form higher order mux like 8:1 mux. Now for an example, let us try to implement a 4:1 mux using a 2:1 mux. To construct a 4:1 mux using a 2:1 mux, we will have to combine 3 2:1 mux together. The end result should give us 4 input pins, 2 control or the select pins and 1 output pin. To achieve the first 2 mux is connected in parallel and then the output of these 2 are fed as input to the third mux, which is as shown. The first 2 mux are connected in parallel and is connected to the same select lines, that is S0. When the select line S0 equal to 0, the first mux selects the input I0 as its output and the second mux selects I2 as its output. So when the select line S0 equal to 0, the inputs to the third mux are I0 and I2. When the select line S1 equal to 0, then I0 is selected at its output, or when S1 equal to 1, then I2 is selected as its output. As we can see from the table, when S0 equal to 0 and S1 equal to 0, input I0 is selected as the output, whereas when S0 is 0 and S1 equal to 1, input I2 is selected as the output. When the select line S0 equal to 0, the first mux selects the input I1 as its output and the second mux selects I3 as its output. So when the select line S0 equal to 1, the inputs to the third mux are I1 and I3. When the select line S1 equal to 0, then I1 is selected at its output, or when S1 equal to 1, then I3 is selected as its output. As we can see from the table, when S0 equal to 1 and S1 equal to 0, input I1 is selected as its output, whereas S0 equal to 1 and S1 equal to 1, input I3 is selected as the output. The figure shows the implementation of the 4:1 mux using the 2:1 mux. We can see that from the implementation of a 4:1 mux from 2:1 mux, we require a total of 3 multiplexers for the design. If we design an 8:1 mux using 2:1 mux, we require 7 mux. Similarly, for 16:1 mux, 15 2:1 mux are needed. 32:1 design requires 31 2:1 mux. Hence, we can draw a conclusion: 2n:1 mux requires 2n minus 1 2:1 muxes. Let us try to better understand the concept of mux tree by looking at another example. That is, we are trying to implement a 16:1 mux using the 4:1 mux. The same selection lines S1 and S0 are applied to the 4:1 multiplexers. The data inputs of the first 4:1 multiplex are I0 to I3. The data inputs of the second 4:1 multiplexer are I4 to I7. The data inputs of the third 4:1 multiplexers are I8 to I11. The data inputs of the fourth 4:1 multiplexers are I13 to I15. Therefore, each 4:1 multiplexer produces an output based on the values of the selection lines, that is nothing but S1 and S0. The outputs of the first stage 4:1 multiplexers are applied as input to the 4:1 multiplexer that is present in the second stage. The other selection lines S2 and S3 are applied to the 4:1 mux. Let's look at the different cases. When S3 equal to S2 equal to 0, when the select line S3 and S2 are both as 0, the output of the second stage comes from the first input depending on the values at S0 and S1. Let's see what are the outputs with respect to the select line S0 and S1. When S0 equal to 0 and S1 equal to 0, input I0 is selected at the output by the mux. When S0 equal to 0 and S1 equal to 1, input I1 is selected at the output by the mux. When S0 equal to 1 and S1 equal to 0, the input I2 is selected at the output by the mux. When both S0 and S1 are 1, input I3 is selected at the output by the mux. Let's look at the next case. That is, when the select line S3 is 0 and S2 is 1. The output of the second stage comes from the second input depending on the values at S0 and S1. Let's see what are the outputs with respect to the select lines S0 and S1. When S0 equal to 0 and S1 equal to 0, input I4 is selected at the output by the mux. When S0 equal to 0 and S1 equal to 1, input I5 is selected at the output by the mux. When S0 equal to 1 and S1 equal to 0, input I6 is selected at the output by the mux. When S0 equal to 1 and S1 equal to 1, input I7 is selected at the output by the mux. Next case, when S3 equal to 1 and S2 equal to 0, the output of the second stage comes from the third input depending on the values at S0 and S1. Let's see what are the outputs with respect to the select lines S0 and S1. When both S0 and S1 are 0, input I8 is selected at the output by the mux. When S0 equal to 0 and S1 equal to 1, I9 is selected at the output. When S0 equal to 1 and S1 equal to 0, I10 is selected at the output. Finally, when both S0 and S1 are 1, input I11 is selected at the output. Next case, when both S2 and S3 are 1, the output of the second stage comes from the fourth input depending on the values at S0 and S1. Let's see what are the outputs with respect to the select lines S0 and S1. When both S0 and S1 equal to 0, I12 is selected at the output. When S0 equal to 0 and S1 equal to 1, I13 is selected as the output. When S0 equal to 1 and S1 equal to 0, I14 is selected at the output. Finally, when both are 1, I15 is selected at the output by the mux. Therefore, the overall combination of the 5 4:1 multiplexers performs a 1:16:1 multiplexer. Let's see at the applications of the multiplexers. So these are basically used in various applications wherein multiple data need to be transmitted by using a single line. In communication system, a communication system has both a communication network and a transmission system. By using a mux, the efficiency of the communication system can be increased by allowing the transmission of data such as audio and video data from different channels through single lines or the cables. When it comes to computer memory, multiplexers can be used in computer memory to maintain a huge amount of memory in the computers and also to reduce the number of copper lines required to connect the memory to the other parts of the computer. In telephone networks, multiple audio signals are integrated on a single line of transmission with the help of a multiplexer. Transmission from the computer system of a satellite multiplexer is used to transmit the data signals from the computer system of a spacecraft or a satellite to the ground satellite by using a GSM satellite. So let's now look at demultiplexers, which is also called as demux. This is a device that takes in single input line and routes it to one of the several digital output lines. The demultiplexer of 2 power n outputs has n select lines, which are used to select which output line to send to the input. The action or operation of the demultiplexer is opposite to that of the multiplexer. As inverse to the mux, demux is one-to-many circuit. With the use of a demux, the binary data can be bypassed to one of its many output data lines. The process of getting information from one input and transmitting the same over one of the many outputs is called as demultiplexing. A demultiplexer is a combination logic circuit that receives information on a single input line and transmits the same information over one of the 2n possible output lines. The bit combinations of the select lines control the selection of the specific output line to be connected to the input at a given instant. The figure illustrates the basic idea of a demux, in which the switching of the input to any one of the 4 outputs is possible at a given instant. Demultiplexer provides its input data a specific direction to flow through. Demultiplexers are also called as data distributors, since they transmit the same data which is received at the input to different destinations. Demultiplexers can be used to implement general purpose logic. By setting the input to true, the demux behaves as a decoder. 1:2 demux. This demux has 2 output channels and have one control signal. When the control signal is 0, the first output channel is selected. When the control signal is 1, the second output channel is selected as the route for the input data. There is also an enable bit which is used for enabling and disabling the circuit, which can be active high or active low. The figure shows the working of a 1:2 demux. When select equal to 0, the input is selected at the output line 0, and when select is 1, the output is selected at the output line 1. The truth table of a 1:2 demux considers input as D and output as Y0 and Y1, and the control signal is S. The truth table of one of the 1:2 demux is as shown. According to the truth table displayed, the output expression is Y0 is equal to S bar D, Y1 is equal to SD. The schematic diagram of 1:2 demux using logic gates can be seen here. Demultiplexers needs AND gates equal to the number of the output channels and NOT gates equal to the number of the control signals. Let's see a 1:4 demux. A 1:4 demux consists of one input line and 4 outputs, and it requires 2 select or the control lines to make the selection. The truth table of a 1:4 demux can be seen. According to the truth table given, the output expression is D0 is equal to I S1 bar into S0 bar, D1 is I S1 bar S0, D2 is I S1 S0 bar, D3 is I S1 and S0. A 1:4 demux can be implemented by using 4 3 input AND gates and 2 NOT gates, which can be shown. The 2 selection lines enable the particular gate at a time. So depends on the combination of the select inputs, input data is passed through the selected gate to the associated output. If S0 and S1 values are 0, 0, then input to the last AND gate becomes high and input is sent at output Y0. When S0 and S1 are 0, 1, then input is sent through Y1. Similarly, for S0 and S1 equal to 1, 0, input is sent through Y2, and lastly, when S0 and S1 equal to 1, 1, then input is sent at Y3. Let's see the applications of a demux. Coming to a communication system, a demux is used to connect a single source to multiple destinations. Demultiplexers are mainly used in the field of communication system. The demultiplexer receives the output signals of the multiplexer and converts it back to the original form of the data at the receiving end. Mux and demux works together to carry out the process of communication. ALU. Demultiplexers are used for reconstruction of parallel data and ALU circuits. Demultiplexers helps to restore the output of the ALU in multiple registers and storage units in an ALU circuit. The output of the data in the ALU is fed as data input to the demux. Each output of the demux is connected to the multiple registers which can be stored in the register. The next one is parallel data. A serial to parallel converter is used for reconstructing the parallel data from the incoming serial data stream. In this technique, several serial data from the incoming serial data stream is given as the input to the demux at the regular intervals. A counter is attached to the control input of the demux. This counter detects or directs the data signal output of the demux where these data signals are stored. When all data signals have been stored, the output of the demux can be retrieved and read out in parallel.